we can continue our lectures concerning the bipolar transistor. I'm just repeating the heavy stuff we have had as a topic in the morning. It is not very easy to digest. Therefore, I'm trying to repeat the most important points. First, a bipolar transistor is set up by two diodes. One diode is here, the second diode is here. The diodes are anti-parallel. That means if you forward bias to one, automatically the second is reverse biased. Point 2. Point 3. You forward bias one diode and you inject the majorities into the base. The base is made so short that these minorities, which were here majorities, can't recombine because the probability is very low. Third, the second diode is reverse biased. Therefore, the minority carrier concentration is 0 at this space charge boundary. This means if you inject majorities and extract all of them after some 100 nanometers, it is very short. Take this into account. Then you have just like a pile of sand. You pile up here, and here you have no sand. So the slope is a straight line. And this slope defines your transistor current. Okay, so what is current? Flow. It is a flow of charges. What is flow? Change in concentration of particles. So if you increase this point to higher values, you have a forward bias. So a forward bias increases exponentially this concentration and therefore the slope, and therefore the transistor current. So this diffusion triangle defines your transistor current. This is the main driver of your transistor current. And this one is sitting on here. Here you get the most current. This one is a minor value because here you have a small slope. This one is a minor value. You have a small slope. But this one is a large value due to the huge injection of carriers. Okay. So therefore, you have also some charges in the base. So we talk about particles, minorities, but we also have charges in the base. And this charge also prevents the transistor to be fast switched completely off. Because to switch off the transistor, you have to pull down this concentration. How? By diffusion. And diffusion is a small process. But a signal is a small deviation. That means a signal is amplified very directly with an exponential value. So the transconductance is an exponential value. But as a power electronics device, it is a very slow device due to the need of completely charging and discharging that stuff. But we will come back to that point later once more. The current is only the sum of the individual current components. So the emitter current consists an hole current component and electron current component. So you make plus in between. The collector current has an hole component and an electron component with a plus in between. And the difference of these two currents is the base current. So the difference, why I have a plus sign, because of the definition of the collector current, which is minus, therefore plus. Okay. So we have the transistor current, that's it. Now, let's learn something based on the parameters of a transistor, of a bipolar transistor. I said here the emitter efficiency. We said that the emitter efficiency is the relation between this current and that current. Now, we have the equations for these currents. If we take the equations, then we get for the emitter efficiency this equation as an approximation. What do you see here for the efficiency of the emitter? It increases if you reduce the width. Yes, that's true, because if you reduce this neutral width, then the injected holes have less probability of recombination there. And this again increases the efficiency. One more. And it is also a function of the doping, always doping relation between emitter and base. What does that mean? If you increase the emitter doping, you increase the efficiency. Yes, sure, because if in the relation you have more holes than electrons, and this in turn means if you have more holes than electrons, then less recombination happens for the holes. Therefore, the efficiency increases. Okay, so you have from the physics of the device a hint what you should do to optimize the device parameters themselves. Okay, let's go on. Let's take a closer look at the base transport factor. Kathy. What was the base transport factor? What portion of the holes in the collector was previously left in the emitter? So we start at the big portion, less holes, and even less holes we have here. And the relation of these two currents is the transport factor. Transport factor. Okay, and the transport factor has a to the square dependence of the width. Yes, sure. If you have less width, you have less recombination. Current gain in emitter configuration. So, what is the emitter configuration? You have a transistor a bipolar transistor referred to the ground here. And what is the current gain? The current between, oops, what has happened? Switch off and switch on, and hopefully it comes back. Yes. So the common emitter configuration, you compare these two currents from the collector and the base. And you see then, if you divide these currents, a smaller width increases the current gain. Yes, you need less base current because it's no more lost. You increase the emitter doping as a relation to the base doping. Yes, the whole flow is dominant and electron backflow is no more dominant. Therefore, we have the initial condition. I have said we will come back later. A high emitter doping, less base doping, and even less collector doping. Okay. The last part, the current gain in common base configuration. How does a transistor look like in common base configuration? You have an emitter, base, collector, and now you compare these two currents. And uh, by nature, you see if we have optimized the transistor that way that it doesn't take away any current in the base, then your emitter efficiency does dominate your current gain. It is roughly 1. And this value is usually larger than 100. Okay, so these were the physical parameters of the bipolar transistor. I don't want to tell more about the physical parameters because we learned the bipolar transistor to use it as a device in circuits, analog circuits. Therefore, we reduce everything from what we have had to these equations. So the collector current is an exponential function of the base emitter voltage. Yes, we know. And here we have a parameter n. The base current is also an exponential function of the base emitter voltage, but it has two different exponential functions. Why? Because first this n is here, and usually the n, this you can extract it from this slope. This n is approximately 1. For the base, due to the very low figures, so we operate in this area, let's say 0.5 to 0.7, in this area. The currents, if you go down with the voltage, are very low in their value. You see it is a logarithmic scale. And in these low values, you have two different emission factors or two different factors in the exponential behavior of a bipolar transistor. The M is the so-called emission factor of the nonlinear base current. The base has also nonlinear parameters, the additional parameters, and these can be seen here. like you have in your intrinsic carrier concentration and the concentration of the majorities. The majorities are dominant, but from low temperatures to high temperatures, the intrinsic carrier concentration somehow crosses the majorities. And then you can see it. This is the other way around. And here you see the non-idealities of the base for very low voltages. Okay. The first parameters you can take a look from are from the so-called Gammel plot. The Gammel plot takes a transistor, a bipolar transistor, and applies between base and emitter and collector and emitter two independent voltage sources and applies the same value to both voltage sources, so that effectively the collector and the collector base voltage is zero, but effectively not short circuited. Why? In order to plot the base current and the collector current individually. So if you inject a base current and if you don't apply any reverse bias, so if you don't apply any reverse bias, what condition do we have? We inject majorities, here we are, but we don't apply any reverse bias. So the space charge is, let's say, here, and this point is here, and this point is the P0 in the N region. You remember? Go to the page 59 or something like that. The minority carrier concentration is then the natural value, but not zero. Okay, so that's the only difference. So the Gammel plot plots this condition. And in the Gammel plot, we have region 1, that's the low current region, the region 2, where we are usually operating our transistor, and region 3 is the high current region. And the beta, the current amplification factor, current gain, is roughly constant in region 2. In region 1, it's dropping. You see this difference? So for low current values, it is dropping. And for high current values, it's also dropping. This current gain between collector and base. Okay. Let's take a look at region 1, the low current region, where we are not usually operating our transistor. From the slope, we can extract the saturation current. From the slope, we can also extract the saturation current from the intersection. And let's take a look how the equation looks like as in a logarithmic scale. The y-axis intercept is the saturation current you can extract from. And from the slope itself, you can extract the non-ideality factor. So you can extract from the slope the M, and from the extraction the saturation current IS. I think it was E. Yeah, okay. And the same game you can do where we are usually operating. The first important factor is the current gain. We assume it to be constant there first. And then we assume that the collector current is a normal exponential function. And the base current is just the collector current divided by beta. Again, the main equation is the collector current, and the derived equation is divided by beta. Okay, so if we talk about the current equations of a bipolar transistor, we talk about this exponential function. Usually n is 1, and from the base current, which is the collector current, divided by beta. That's all. Very much simplified. And the high current region, that's very important and very delicious. Not many people on the world who use bipolar transistors know what high current means. So you can be proud if you understand it, then you can tell it to usually all engineers, new stuff, if you talk to them. um, what is high current? If you buy a bipolar transistor, you can usually say, if you have VBE and you can IC, the exponential function, you expect it is going on and on and on. Yes. But what is the collector current? It is the current which is injected through the base into the collector and collected in the collector. Okay, so what is an electron doing? This region is neutral. This region is the space charge region of the emitter base area. Okay. In the space charge, the electrons are drifting. In the rest of this area, it is so-called a resistive area. There, they are also drifting. The electrons are minorities in the p area. There, they are diffusing. And at the space charge region boundary of the base towards the collector, this electron concentration is 0. Okay. And these electrons are now drifting through the space charge region of the collector. Now the important point happens. What we have learned from the collector doping, so the doping concentration in the collector, we have learned that it is smaller than the doping concentration of the base. And we have learned that this concentration is smaller than the doping concentration of the emitter. Yes, so in easy words, we have the least concentration in the collector. What does a space charge region means? It means charges in the space. Yes, the name gives you what I mean. These charges are there. Your electrons are there. Why? Because they are flowing through the space charge. And in the time of being there, they neutralize, in the meantime, the space charge. What does that mean? If they neutralize the space charge, then no force takes them out of the base. So in one time, or at a certain value of a current, so a certain value of a current, so electron flow through the space charge, there is no more additional force to take out these electrons from the base. And therefore, your collector current doesn't increase further exponentially. So this linear slope is an exponential growth. Okay. Therefore, due to this neutralization process, you say we are in a high current regime of the transistor. Therefore, in the data sheet of a bipolar transistor, the maximum value where you can use this device is also stated. It is important for the person who is using it. What does this intersection means? This means if your current level here is 10 ampere, you have to put also 10 ampere into the base. That's nonsense. Usually you say I have here 10 ampere divided by 100, 100 milliamp, right? Yes. So you put 100 milliampere into the base, and with this low current value, you control the 10 ampere. And if you overdrive the transistor, you have to put the same value into the transistor, and that's nonsense. Okay, so that's the first part of the high current region. The second part, that's very obvious if you have understood the diffusion triangle. What does it mean? You inject here holes, yes, and you extract all of them. What happens if you also forward bias the base collector diode? Then you inject from the collector to the base also some holes. Okay, you can do that. But at some point, the slope is zero. And what does it mean? Slope zero, no current. This means that this can also happen to you unintentionally. Why? You apply, let's say, here 0 volt, and here, let's say, 2 volts. And between base and collector base and emitter, you apply 0.7 volts. Let's assume. So you say my internal bias is 0.7 volts, and my reverse bias, one moment, my reverse bias is now 1.3 volt minus my reverse bias. Because from these 2 volts, I just have only 1.3 volts left for reverse biasing this diode. This region of the collector is ohmic. This means you have a voltage drop in this direction. This means the internal reverse bias can go to 0 or also can get plus 0.7 volts. And if this internal bias is getting forward bias, then your current is also no more increasing because your diffusion triangle gets a lower slope due to the back injection of the majorities being than minorities in the base. This means this ohmic region you have to take into account when the current is flowing through the technical current is flowing through the transistor. This is the technical current. And the ohmic region produces additional voltage drop. And you have to reverse bias the intrinsic diode of the transistor in order to have a proper operation. Therefore, you have two limitations. One limitation is due to the doping. The second limitation is due to the ohmic region. Full stop. And we operate our transistor here. We operate our transistor in the active forward region, in the active region. The one diode is forward biased, the other diode is reverse biased. So we are here. If the collector has a lower potential than the base potential, then you start to forward bias your collector. And this is the reason why the current is going towards zero. So at collector emitter is equal to zero, see here. So if, therefore, an unnatural color, if this is zero, and if this voltage is 0.7 volt, then this voltage is 0.7 volt, and also this voltage is 0.7 volt. So both diodes are forward biased the same with the same value because this potential is zero. Okay, therefore the collector current is zero and the collector current increases and gets to this area, into the active area. And if you take the transistor and use it the wrong side down, then the previous collector is now the emitter. The previous emitter is now the collector. And so if you accidentally use it the flip side down, upside down, then the current gain is no more good, and the breakdown voltage is no more good because all the space charge areas are now the wrong way around. Okay. It is very important to know this. If you're a circuit designer, you should keep in this area very carefully. Don't go below the collector emitter voltage below the base emitter voltage in order to prevent the back injection of carriers into the base from the collector. You should prevent this node to go up from the diffusion triangle. You have to prevent that. If you don't prevent that, your charge is increasing and your transistor is getting slower. Okay. And let's talk now about this area in more detail. If the collector emitter voltage is below the value of 0.7 volts roughly, then the collector base and the emitter base are both forward biased. Emitter base has a large injection, so this is again the diffusion triangle. And due to this injection of electrons into the base, this point also increases. Therefore, the slope decreases. And therefore, your current decreases. That's the chain of causality. So the collector emitter voltage drops, the base emitter voltage increases, the slope of the diffusion triangle decreases, and the slope is the first derivative is the current flow, yes, and therefore the current flow decreases. Okay, so here we don't operate. We do operate here, and there we have again this equation from the Gamow plot, you know, but plus one factor or coefficient. And this coefficient is a function of the collector emitter voltage. So like in the MOSFET, you can assume this is constant, but in reality you have a certain slope, like in the MOSFET. The reason for this increase of the current was in the MOSFET the channel length modulation. Here, it has a complete different reason physically. I will explain. So again, you have a MOSFET, you have a transistor, you have a current source. Yes, and the current source is not idea. So you have a current source, and in parallel, you have a certain resistance, like in the MOSFET. This intersection point, if you interpolate this slope, has a name. It is called early voltage. Mr. Early has said, this is my voltage. And we say, yes, it's early voltage. And the PEEP reason for that is this. Take a look on this sketch yourself. First, yourself. Follow these two Arbeitspunkte, these two bias points, follow up these two bias points, and follow up this chain of causes. First, take a look at the bias point 1. If we have a bias point 1, we have a certain collector emitter voltage. If we have a certain collector emitter voltage, we have therefore a certain collector base voltage. If we increase the collector emitter voltage, we increase the reverse bias of the collector base voltage. We increase it. The reverse bias is increased. This means the space charge boundary for this diode is also pushed into the base, also into the collector. This push into the base of this space charge boundary changes the point where the concentration of the minorities gets 0. This change of the location of 0 changes the slope. The slope increases. And if the slope increases, your collector current increases. So the increase in the collector current due to the increase of the collector emitter voltage is caused by the space charge boundary pushed into the base. And what we have learned for this P-N diet, if you increase the P and reduce the N, this push is reduced. And therefore, due to this early effect, due to this space charge boundary, so due to, one moment, it is called X. Do you know the index? X base at the collector side. I don't remember anymore. Call it X bota. It has a name. Now, due to the X bota index, which is a function of the doping in the base, you increase this doping level. And therefore, to reduce this slope and to increase this early voltage, you reduce the doping level in the collector and increase the bota doping in the base. Only for the sake of this slope. Now you can understand in which dilemma a device designer is sitting in. A device designer wants to have a flat slope. Then you can say, let's reduce the doping level in the collector. Then the second designer says, I want to have a very high current level. And this can be made with doping the collector with higher values, because this neutralization of the space charge is a function of the doping level in the collector. So if you increase the doping level, you increase the number of space charges, so you can put more electrons through the space charge before it is neutralized. Therefore, these two factors, the maximum current through the transistor and the early voltage, are contradicting themselves. And a service provider for integrated circuits technology, so it's called foundry service provider, decides certain values for the collector doping. And you can read their decision. Okay, so that was the early voltage, the reason for the early voltage. I have put that here. The second voltage is higher, therefore the reverse voltage is higher, therefore the second base, neutral base width is lower, therefore the slope is higher, and therefore the current is higher. That's the reason. So that's the short version of my last 5 minutes of talk. Okay, let's go on. Equivalent circuit. Let's push back all these stuff we have learned and concentrate on simplified circuits. In the common emitter configuration, you can say that your base emitter is just a diode. Yes, it's true. And you can then say your collector current is just a multiplication by beta of this current. Yes, that's true. So that's the most simple large signal circuit, equivalent circuit. Um, a further, more simplistic but no more very accurate one is this one. As you know that, not Siri, no, not today. As you know that VBE is a function of IB, the current of the base, is a function of the base emitter voltage, and an exponential curve looks like this. And if you say that this is not like this, but it is like this, then you can say I have 0.7 volt, that's it. So in the very first glance at a circuit, you can say the base emitter voltage is 0.7 volts or 0.6 volts. Okay, and the current in the collector is just the value of this current times beta. This is also valid if you take into a large circuit diagram. This you can do. Okay. But let's be more realistic. So in the circuits, in the small signal equivalent circuit. So now we go to the small signal equivalent circuit diagram. In the small signal description, the component values are derived by a small deflection at the operating point. Yes, a small deflection. So again, we have a large signal curve. In the large signal curve, we have our Arbeitspunkt, our Schwäbisch Arbeitspunkt. And one moment. And in this operating point, we have a slope. And this slope, here, how we get that? This slope is the first derivative of an exponential function. We have had this type of proceeding in the MOSFET. But the first derivative of an exponential function is its internal derivative of the internal value, so here, and the external value here. And what is the first derivative of an exponential function? It's the exponential function. And what is the first derivative of the internal function of the exponential function? It is 1 over Vt, the temperature voltage. That means if you derive the IB current, you get the IB current because it replicates its behavior, but divided by Vt due to here. That's all. And the result is IB divided by Vt. Isn't that delicious? If you really take a look at a curve like this, you can say the slope at any location is calculated by the large signal value divided by 25 millivolt. So you can calculate it by hand. Now, it comes a second statement. Where is the physical property of the transistor? Its doping level, its area. Where is it? It's gone. This is the best part of a bipolar transistor usage. All bipolar transistors behave basically the same. If you take this size of a bipolar transistor or this size of a bipolar transistor, if you have 0.6 milliampere base current, basically you have a certain base emitter voltage and you have the same slope. So the bipolar transistors are interchangeable from their basic behavior. Not the parasitics, for sure, but basic behavior. We have no V to L. We have no oxide capacitance. So you know the beta was V to L times mu times C ox. You know? Nothing. There is nothing there. Okay? Okay, now if you multiply the base current with beta, you get the collector current. Now you have the most important diagram of a transistor again. The base emitter voltage is a function, no, the collector current is a function of the base emitter voltage. And it is again exponential. And again, you have a certain slope. And again, this slope is the first derivative of the collector current, and the result is the collector current itself divided by Vt. So the transconductance of a transistor is just your operating point's current. So your bias current defines your transconductance. Let's calculate the values. What is this resistance here? Let's assume the beta is 200, typical. Let's assume your bias current is 10 milliampere. That's also usual for high frequency applications. Then the equation is Vt divided by Ib, and that's equal to what is the equation of Vt? The Boltzmann constant times the temperature divided by Q times 1 divided by Ib. What is Ib? Ib is, let's assume that's 25.6 millivolt, the temperature voltage. The Ib is Ic divided by beta. Now we have everything. Now you can calculate the base emitter differential resistance. The differential resistance is the slope at this curve. Can you give me the value? Again, please. Millivolt, right. Great. 512 ohm. So the input port, the input port of a bipolar transistor looks like a resistor RBE having 500 ohm. Okay, that's a fact. And if you change the technology, and have the same bias, you have the same resistance as a slope, as a differential resistance. Okay. Um, Now let's take a look at the GM, at the transconductance of the transistor. The GM is IC divided by VT. The current is, if not otherwise stated, the same. The temperature voltage we keep to have the same value. Give me the transconductance value, please. 1 over ohm, or 0.391 Siemens. Okay. You say, is that large? That's gigantic. It's huge. Compared to MOSFET, it is 1,000 times larger. At the same values you apply in the MOSFET. That means if you have apply a voltage signal at the base, you get 100 to 1,000 times larger current change in the transistor using bipolars. Therefore, bipolars have had a high time, a very prominent time in technology. But getting the transistors in the MOSFET smaller and making possible more complex circuits, you can even generate 2 gigahertz amplifiers using MOSFET technology. But this is only possible getting high sophisticated, large scale, small transistors like it is made by Intel, AMD, TSMC. Okay? But at the beginning, your technology was, your feature width was 1, 2 micrometer. And with 1, 2 micrometer feature width, you made several gigahertz bipolar transistors and 1-digit megahertz MOSFETs. That means at the beginning, the gigahertz range was only reachable by bipolars. So bipolars are also more, yeah, they are cheaper for the same frequency application. And today, let's take a look at IEEE Explore. So you are students and you have access to IEEE Explore. This is a database for all publications in the IEEE range. And there, please type in silicon germanium and gigahertz. Silicon germanium, so it's like a silicon transistor, but with some added germanium inside. And type in gigahertz and type terahertz also, gigahertz or terahertz. Then you will find out that 70 or 100 gigahertz applications are possible with normal transistor sizes. That's really exorbitantly interesting. Just take a random look in the literature range. Okay. Now we have this transconductance. It is huge. Now let's take a look to 1 over this transconductance. What is 1 over the transconductance? It is the resistance if you take a look into the emitter electrically. What is the resistance if you look electrically into the emitter? Why? It is this current because the current which is flowing through the collector current, is flowing out of the emitter. It's the emitter current. Therefore, so the delta IC as a function of a VPE is also the DIC as a DIE is a changing VBE. So you can say the emitter resistance is just 1 over the transconductance. And the value, you can give me it one more press. So if you look electrically into the base, you see 500 ohm. If you look electrically into the emitter, you see 2.5 ohm. That means all these impedance values are important in a circuit diagram as a location where you are using it. Where you need high impedances, um, if you don't want to load a source. Where you need low impedances, if you want to have high frequency applications. I'm now saying something interesting. High frequency applications. What does that mean? Every limitation of a circuit is given by its resistance and its capacitance. It's a low pass filter. What happens if one resistance is reduced? Your corner frequency is increased by the same factor. Therefore, you control the emitter for high frequency applications. You control the base for low load applications. But this will be a later topic later. I think we already passed